Hey, welcome to Kinetics, Part 2. This time I'm going to talk about second order rate laws. Just give you a background. Within kinetics, we're talking about how fast a reaction goes, the rate at which it proceeds. And so we have first order rate laws, and we talked about a first order rate law is going to look something like this. The rate is going to equal the concentration to the first power. And so we don't have to write it, but we can just put it there. So that means that if I doubled the concentration, I'll double the rate. Now second order, so this would be first order. And we discussed that in the last video and showed the differential and integrated rate law equations for those and solved a problem using the integrated rate law. And so then if we look at the second order rate law, it's going to look like this. And second order just simply means to the second order. And so what would happen if you doubled the concentration here? Well, it would go to the second power, so it would quadruple the rate. And so the only way that these can be determined, can be found, is by experimentation. You can't mathematically figure this out. You can't look at them and figure it out. You have to do it by experimentation. The reason for that is not every reaction proceeds as we write it out on paper. A lot of times there's elementary steps within those reactions. And so if one of those elementary steps has a different rate, then it slows everything else down, or has a slower rate. It slows everything else down to match that one, because it sort of bottlenecks there. And so we wouldn't know that it has elementary steps unless we do experiments and measure the actual rate change over time. So we're going to look at second order rate laws today, and if you were to take and graph these out, it would give you a similar kind of thing as you saw with first order. And so what would happen is the concentration would change over time, like so, and it would just do so rapidly as the concentration change. The rate would go in a second order. But it would, the graph would look very similar to a first order graph in that sense. And so what we need to do is we need to come up with an integrated rate law, and using calculus that allows us to be able to solve parts of these simply. Okay, so not going to go over the calculus of it all, but what you're going to do is essentially take the second order rate law and apply calculus. You're going to integrate both sides, and you're going to do that so that you can take this equation and turn it from this sort of a line into a straight line. And so the sort of straight line you end up getting with the integrated rate law looks something like this. And so it's got a positive slope as opposed to the first order rate laws that had a negative slope. And so this is what it looks like. If you are to take and integrate it, you would get something like this. 1 over the concentration at a given time equals the constant of that reaction times the time, plus 1 over the concentration initially. Okay, and then similar, what we're doing is we're trying to simplify this, and so this equation also is a linear equation. We see it gives us a straight line on the graph, so it's a y equals mx plus b scenario, where this is your y-intercept, this is your x coordinate point, this is your slope, and this is your y coordinate point on your graph. So you could easily use those to graph these out. And this is really helpful because a lot of times in the lab, when you take data, like say you're writing down your data in the lab, you're not going to be able to measure the rate. I mean, you're not going to be able to measure all of these different things, but what you can measure is you can measure time real easily, and so you could easily measure time. And then at certain time intervals, you could stop the reaction and measure concentration. So you could get time and concentration really easily. So let's say that this is our time and concentration graph. So let's say this is time in seconds. So if we go 50 seconds, let's say we get 0.00787. And just quickly going to make a little graph for you. And let's see that that ends up at 0.0649. Well, if I take my equation, and I haven't even said what equation this is, I'm just making this up. But let's say it looks something like this. If I take this and I take this time and this concentration and I plot it in these graphs, I can determine whether it's first order or second order from this data. And so I'd simply do that by saying, okay, the concentration change in a second order equation is going to be 1 over the concentration, so because that's what I have here, and over time. In a first order, you saw that it was the natural log of the concentration. So I'm going to just put m there to symbolize molarity over time. So if I took and I said I took this and I divided 1 by 0.01, I plotted that and 0, and then 1 by 0.0087, plotted that and 50. What I would find is that I would end up getting a straight line that looks like this for this data. And if I took the same data and I plugged it in here and I took the natural log of 0.01 with 0 and made that point, and the natural log of 0.007 and made that point, I would get something of a curved line. And so what you can do is you can just take the data and you can plug it into a second order graph or plug the data into a first order graph, and whichever one gives you the straight line, that's your winner. Okay, woohoo, yay, winner. And so this one right here, if you take this data, it tells you that this is a second order reaction. So using the integrated rate law and components, it's a really, really simple way to take data in the lab and to figure out, do I have a second order or do I have a first order? So you don't have to figure out rates, you don't have to do all that and know whether it's quadrupling, blah, 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 anything. All you got to do is take the time, measure concentrations at different time intervals, try graphing it in both, whichever one gives you the straight linear line. Well, there you are. It matches up to the integrated rate law for second order, and that's the winner. And so we'll draw a smiley face right there. So the data in this case confirms second order. In the next video, what I'm going to do is I'm going to explain half-life for first and second order rate laws.